Have you ever wondered how a computer can look at a photo and tell a cat from a dog? Well, the magic behind it is something called the convolutional layer. It is the absolute core building block that lets AI see the world. And today, we're going to break down exactly how it works. Let's dive in.
Okay, I know what you're thinking. You see a slide like this, jam-packed with math, and it's a little intimidating, right? But I promise you, the actual idea behind all of this is incredibly simple. And by the end of this, you're going to get it completely. So all this magic happens inside something called a convolutional neural network, or CNN for short. You gotta think of these as the absolute powerhouses of computer vision. Their entire job is to take an image and just systematically break it down to find the most important features inside.
At its heart, what a CNN is really doing is pretty straightforward. It takes a raw image, just a grid of pixels, applies a set of mathematical weights to it, and by doing that, it pulls out the key patterns. You know, the edges, the textures, the shapes that make that image what it is.
To really wrap your head around this, we need to meet the three main characters in our little story here. Think of them as the essential ingredients that make the whole recipe work. So first up, you have the input image itself. That's just a grid of pixel values. Nothing fancy. Second, you have the star of the show, the kernel. This is our clever little feature detector. And third, you have the feature map, which is what we get at the very end of the process.
And this slide shows the flow perfectly. That kernel, the little yellow block in the middle, it acts just like a specialized magnifying glass. It slides over the input image looking for one very specific thing, and then it creates a new, much simpler output map that basically highlights everywhere it found that pattern. All right, so we have our ingredients. Now let's step into the kitchen and see exactly how they all come together to create that final dish, the feature map.
So what is this kernel, really? It's just a small grid of numbers, a tiny matrix of weights. But here's the cool part. It's been specifically trained to spot a single tiny feature. So one kernel might be an expert at finding vertical lines, while another one is a total pro at finding a certain curve or texture.
Now check this out, because the math is way simpler than it looks. Take a look at that top example. The kernel is placed over a little patch of the image. You just multiply each number by the one it's sitting on top of. So 0 times 2, -1 times 2, 5 times 3, you get the idea. Then you just add up all those results, and boom, you get one single number, 7. That's literally it.
Let's just run through that one more time to make it stick. You place the kernel, you multiply, you add it all up, and you put that final number into a new grid. Then you just slide the kernel over one spot and do the exact same thing again, and again, and again, until you've scanned the entire image. And that new grid you're building with all those numbers? That's your feature map. A high number on this map means, hey, the kernel found a really strong match for its feature right here. A low number means, not so much. So it's basically a treasure map for a specific visual pattern. How clever is that?
Now, this whole process isn't just set in stone. We've actually got a few key parameters we can tweak. Think of them as dials and levers to really fine-tune how this whole thing behaves and what kind of output we get.
The three main controls we have are depth, stride, and padding. Now, depth is just about how many different kernels we're using at the same time, like one looking for vertical lines, another for curves, another for a certain texture, all at once. But for now, let's really zoom in on the other two, stride and padding.
Stride is super simple. It's just how many pixels the kernel jumps each time it moves. So a stride of 1, like you see on the left, means it shuffles over just one pixel at a time. You get a ton of overlap and a big, detailed output map. But a larger stride, like 2, means it's taking bigger hops. You get less overlap and a smaller, more condensed output.
Padding solves a problem you might not have even thought about. See, without it, that kernel can't really analyze the pixels that are right on the edge of an image, so we just lose that information. The fix is actually really simple. We just add a border of zeros all the way around the outside. This zero padding lets the kernel scan the entire image corner to corner, and it also lets us control the size of our final feature map. Okay, so we've been deep in the weeds on the how, the multiplying, the sliding, all the controls. But let's take a step back for a second and ask the most important question of all. Why are we going through all this trouble in the first place?
So what is the end game here? Why does this whole complicated-sounding process actually matter?
Well, it really boils down to two huge benefits. First, size reduction. We are taking a massive image and condensing it into a much smaller map that's way easier for a computer to work with. And second, and this is the big one, feature detection. We're turning raw, meaningless pixels into something useful, a map of where the important stuff is. And here's the truly mind-blowing part. These features build on each other. The first layer of kernels finds simple edges. The next layer takes those maps and combines them to find corners and curves. The layer after that combines those to find things like eyes and noses, until finally the network can say, hey, that's a face.
This quote from the source material really hits the nail on the head. By using the exact same kernel across the entire image, we give that little feature detector a chance to find its target no matter where it's hiding.
And this ability has a name: translation invariance. It's a fancy term for a really simple idea. The network can recognize an object, or feature, no matter where it is in the picture. A cat's ear in the top left or the bottom right. It doesn't matter. The cat ear kernel is going to find it. And this is absolutely critical for recognizing objects in the real world.
So, to wrap it all up, the convolutional layer is this incredibly powerful tool. It uses a small, sliding kernel to do simple math over and over again, creating a feature map that both shrinks the image and highlights key patterns. This is how AI builds up an understanding of an image, from simple edges to complex objects, and learns to find them anywhere. But this leaves us with a final, pretty interesting question. In this process of simplifying an image, what information might we be losing? It's that trade-off between detail and understanding that sits at the very heart of computer vision. Thanks for watching.